What if I told you that, right now, photons of light are hitting your eyes that have traveled for billions of years across the universe? Yet from the perspective of those photons, no time has passed at all, not a single nanosecond. In fact, from light's point of view, the entire journey from the surface of a distant star to your retina happened instantaneously. The photon was emitted and absorbed in the same moment. Zero time elapsed. And here's what will absolutely shatter your understanding of reality. Light doesn't experience change, time, distance, or even existence in any way you can comprehend. Light exists in a frozen eternal now, where the Big Bang and the heat death of the universe occur simultaneously. I'm not talking about some mystical interpretation or philosophical metaphor. This is a direct consequence of Einstein's special theory of relativity, confirmed by every experiment we've ever conducted. Light doesn't experience time. It cannot. And once you truly understand why, everything you think you know about the universe will never be the same. You'll realize that our entire human experience of reality, time passing, things changing, journeys across space, is just one limited perspective in a universe that looks radically different depending on how fast you're moving. By the end of this video, you're going to understand something that most people never grasp in their entire lives. You'll see why the universe is far stranger than you ever imagined, and you'll never look at a ray of sunshine the same way again. But before we dive into the mind-bending physics, do me a favor. Smash that like button, hit subscribe, and down in the comments, tell me where you're watching from and what time it is right now. I want to know. Are you experiencing this moment from Tokyo at midnight? London in the afternoon? São Paulo in the morning? Because unlike light, we're all experiencing time passing right now together. Let's find out why light doesn't get to join us. Let's start with something you think you understand. Speed. You're probably sitting down right now, maybe on a couch or at a desk, and you feel stationary. But are you really? The Earth is spinning at about 1,000 miles per hour at the equator. We're orbiting the Sun at 67,000 miles per hour. The solar system is moving through the galaxy at 514,000 miles per hour. And the Milky Way itself is hurtling through space at 1.3 million miles per hour. So which speed is your real speed? Here's the twist that changes everything. There is no real speed. There's no absolute reference frame in the universe. Speed is always relative to something else. When you're sitting on a train and another train passes going the opposite direction, you feel like you're moving faster, right? That's because you are relative to that other train. But relative to the ground, you're moving at whatever speed your train is going. Both perspectives are equally valid. This isn't just a quirk of perception. This is fundamental to how the universe actually works. Now, before Einstein came along, everyone assumed that while speed might be relative, time was absolute. A second was a second for everyone, everywhere, no matter how fast they were moving. Newton built his entire physics on this assumption. Time flowed like a river, uniform and unchanging, independent of anything happening in the universe. This seems obvious, right? When you look at your watch and I look at mine, we should see the same time passing. But in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that demolished this common-sense assumption. He started with two simple principles. First, the laws of physics are the same in all reference frames that aren't accelerating. Whether you're standing still or moving at constant velocity, you'll get the same results from any physics experiment. Second, and this is the kicker, the speed of light in a vacuum is always the same for all observers, regardless of how fast they're moving. Always 299,792,458 meters per second, no matter what. Think about how weird that is. If you're standing still, and I shine a flashlight, you measure the light going at light speed. Seems normal. But what if you're on a spaceship traveling at half the speed of light, chasing after that same beam of light? Common sense says you should measure the light going slower, right? Like if you're running after a car, it looks like it's moving slower relative to you. But no, you still measure that light beam going at exactly light speed, the same speed as the person standing still measured. This seems impossible. It violates everything our intuition tells us about how motion works. Einstein realized that for this to be true, something had to give, and what gave was time itself. Time had to be flexible, stretching, and compressing, depending on how fast you're moving. This is called time dilation, and it's not a theory anymore, it's measured reality. We've put atomic clocks on airplanes and flown them around the world, and when they landed, they showed less time had passed than identical clocks that stayed on the ground. GPS satellites have to constantly correct for time dilation because they're moving fast enough that time passes differently for them than for us on Earth. If we didn't account for this, your GPS would be wrong by several miles within a day. Here's an analogy that might help. Think of space-time like a video game with a speed limit, the speed of light. Imagine everything in the universe has a velocity through space-time, and that velocity is always the same total amount. You're always moving through space-time at light speed. Always. But here's the trick. You can divide that velocity between moving through space and moving through time. When you're sitting still in space, all your velocity is directed through time. You're experiencing time at the maximum rate. But when you start moving through space, some of that velocity gets redirected. You're now moving through space faster, which means you must be moving through time slower. The faster you move through space, the slower you move through time. And here's where it gets insane. Light is moving through space at the maximum possible speed. That means all of its velocity through space-time is directed through space. None is left for time. Light doesn't move through time at all. From a photon's perspective, time doesn't pass, not even a little bit. This isn't an approximation. This isn't time passes really slowly for light. Time doesn't pass at all. The photon exists in an eternal frozen moment where its emission and absorption happen simultaneously. But wait, it gets even stranger. We're just getting started, and I need you to stick with me because what comes next is going to completely reshape how you understand existence itself. Let me ask you a provocative question. What is time? No, really. Stop and think about it. You experience time passing. You remember the past, experience the present, anticipate the future. Time seems like the most obvious fundamental thing in the universe. But what actually is it? The ancient Greeks had two concepts of time. Chronos was quantitative time minutes, hours, years. The kind you measure with a clock. Chronos was qualitative time, the experience of time, the feeling that some moments last forever while others fly by. But both concepts assumed time was a thing, a dimension in which events occurred, flowing steadily from past to future. Newton agreed. He wrote, "Absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external." Time was the stage on which the universe performed. It existed independently, flowing at the same rate everywhere for everyone. This view dominated physics for over 200 years. Then Einstein showed up and said, "No, time isn't absolute. Time is relative. Time is part of a unified four-dimensional structure called spacetime. You can't have space without time or time without space. They're woven together into a single fabric. And here's the critical insight. Movement through space and movement through time are connected in a precise mathematical way. Let me introduce you to the Lorentz transformation, because this is where the math gets beautiful and terrifying. When physicist Hendrik Lorentz was trying to understand how light behaved, he discovered a set of equations that describe how measurements of time and space change when you switch between reference frames moving at different speeds. These transformations include something called the Lorentz factor, which is calculated as 1 divided by the square root of 1 minus velocity squared, divided by the speed of light squared. Here's what this means in practice. Imagine you're on a spaceship, traveling at 86.6% of the speed of light. That's really fast, about 260,000 kilometers per second. Plug that into the Lorentz factor, and you get 2. This means that for every 1 year that passes for you on that spaceship, 2 years pass on Earth. Time literally runs half as fast for you. Clocks tick slower. Your heart beats slower. Your thoughts happen slower. But you wouldn't notice anything unusual because everything slows down together, including your perception. Now here's where it gets mind-blowing. What happens when you go faster? At 99% of the speed of light, the Lorentz factor is about 7. Time passes 7 times slower for you than for Earth. At 99.9% of light speed, it's 22 times slower. At 99.99%, it's 71 times slower. You're seeing a pattern here, right? As you approach the speed of light, time dilation approaches infinity. And at exactly the speed of light, the Lorentz factor becomes 1 divided by 0. It's infinite. Time dilation is infinite. From light's perspective, time doesn't just slow down to almost nothing. It stops completely. The denominator in that equation becomes 0, and you can't divide by 0. The math breaks down because you've reached a boundary condition where the normal rules no longer apply. Think of it like this. Imagine you're walking toward a wall that gets higher the closer you get to it. When you're far away, it's ankle height easy to step over. As you get closer, it's knee height, then waist height, then over your head. As you approach the wall, it stretches toward infinity. You can get arbitrarily close, but you can never actually reach it or go beyond it. That's what the speed of light is like for anything with mass. But light itself is already at the wall. Light exists at the boundary condition where time stops. But there's another mind-bending consequence of special relativity that we need to talk about: length contraction. Not only does time slow down as you go faster, but distances also shrink in the direction of motion. At that spaceship speed of 86.6% light speed, distances are compressed to half their normal length. At 99.9% light speed, distances shrink to just 4.5% of their normal length. And for light traveling at exactly light speed, all distances in the direction of motion contract to 0. From a photon's perspective, there is no distance between its point of emission and its point of absorption. The photon is emitted and absorbed at the same location, in the same instant. Let me paint you a picture of what the universe looks like from a photon's point of view. A photon leaves the surface of a star 10 billion light years away. From our perspective on Earth, that photon travels for 10 billion years, crossing an incomprehensible distance through the vastness of space, surviving the expansion of the universe itself, until it finally enters a telescope and gets absorbed by a detector. That's an epic journey through space and time. But from the photon's perspective, it was created and destroyed in the same instant at the same location. The 10 billion light years of space contracted to 0 length. The 10 billion years of time dilated to 0 duration. The photon didn't experience a journey. It didn't experience anything. In the photon's reference frame, if we can even call it that, the entire universe in its direction of travel is compressed to a flat plane of 0 thickness, and all of cosmic history happens simultaneously. This is why I said at the beginning that light doesn't experience change. Change requires time. Change is the difference between one moment and another moment. But if no time passes, there are no different moments. There's only one eternal now. Light exists in a timeless state where past, present, and future are meaningless concepts. Are you starting to see why this is so profound? Now, some of you might be thinking, okay, but we use light to see change happening all the time. I watch videos, I see things move. I use light to observe events unfolding. How can light not experience change if we use it to detect change? This is a brilliant question, and the answer reveals something deep about the nature of observation and perspective. Here's the key. Light carries information about change, but it doesn't experience change itself. When you look at a video on your screen, photons are being emitted from the screen, carrying information about what colors different pixels should be at different times. The information changes first. This pixel is red, then blue, then green. But each individual photon doesn't experience that change. Each photon exists in its own timeless instant, carrying one piece of frozen information from emission to absorption. Think of it like a series of photographs versus a movie. From our perspective, we see the movie a continuous flow of changing images. But break it down into individual frames, and each frame is a static photograph, unchanging in itself. The motion exists only when we compare multiple frames. Similarly, the change we observe with light exists only because we're comparing multiple photons, multiple events, from our time-experiencing perspective. But each photon individually exists in a timeless state. Let me introduce you to physicist Hermann Minkowski, one of Einstein's former teachers, who in 1908 made this absolutely profound statement. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Minkowski realized that we should think of the universe not as three-dimensional space that changes over time, but as a four-dimensional spacetime where all events, past, present, and future, exist together in a unified structure. This is called the block universe theory, and it's a natural consequence of relativity. Imagine the entire history of the universe laid out like a loaf of bread. Each slice represents all of three-dimensional space at one instant of time. From our perspective moving through time, we experience one slice after another, creating the sensation that time flows. But from a four-dimensional perspective, all the slices exist simultaneously. Your birth, your childhood, your current moment reading this, your death, and every moment of the universe, from the Big Bang to its ultimate end, all of it exists right now in the block universe. For light, moving at light speed, this block universe is collapsed even further. Not only are all moments simultaneous, but all locations in the direction of travel are also the same location. A photon doesn't experience a four-dimensional space-time. From its perspective, space-time collapses into something like a two-dimensional plane, perpendicular to its direction of travel. It's so far beyond our experience that we struggle to even describe it with language. But here's something that's going to blow your mind. According to special relativity, events that are simultaneous for one observer might not be simultaneous for another observer moving at a different velocity. This is called the relativity of simultaneity. Imagine two events happening on opposite sides of the galaxy. From Earth's reference frame, they happen at the same time. But from a spaceship traveling at high speed, one event happens before the other. Both perspectives are equally valid. There's no objective now that extends across the universe. Different observers carve up spacetime into different sets of simultaneous events. So when I said that from light's perspective, all of cosmic history happens simultaneously, I wasn't exaggerating. For a photon, the concept of before and after doesn't exist. The emission of that photon from a star 10 billion years ago and its absorption in your eye right now are the same event. They're not separated by time or space from the photon's perspective. The photon doesn't have a during its journey because the journey has zero duration. Now, here's where we need to address something important. Can we really talk about light's perspective or a photon's reference frame? Technically, physicists say no. A reference frame, by definition, is a coordinate system in which you can describe events using spatial coordinates and time coordinates. But for light moving at light speed, the Lorentz transformation becomes undefined. You can't construct a valid reference frame traveling at the speed of light because the math breaks down. However, we can talk about what happens in the limit as you approach light speed. We can describe what happens to time and space as you get closer and closer to light speed. And we can see that in the limit, Time dilation approaches infinity, and length contraction approaches total compression. While we can't technically say, this is what light experiences, we can say, this is what the universe looks like in the limit as you approach light speed, and in that limit, time stops and distance vanishes. Some physicists are uncomfortable with even this description, arguing that it's meaningless to talk about light's experience or perspective, and they have a point. But I think there's value in pushing our understanding to these boundary conditions, even if the language we use isn't perfectly rigorous, because it reveals something profound about the structure of spacetime itself. Are you still with me? I know we're getting deep into the physics here, but stay with me because we're about to explore something even more mind-bending. How do particles even become light in the first place? And what does it mean to say a photon is emitted and absorbed? Let's talk about what light actually is, because understanding this will make everything else even more profound. Light is electromagnetic radiation, a self-propagating wave of electric and magnetic fields that oscillate perpendicular to each other and to the direction of travel. But light is also a particle called a photon. This is the famous wave-particle duality of quantum mechanics. In 1900, Max Planck was studying black-body radiation, the light emitted by hot objects, and he made a revolutionary discovery. He found that energy wasn't continuous, but came in discrete packets, or quanta. The energy of each quantum was proportional to the frequency of the light, with the proportionality constant being what we now call Planck's constant. This was the birth of quantum mechanics. 5 years later, Einstein, yes, him again 1905 was quite a year for Albert, took Planck's idea further. He proposed that light itself comes in these discrete packets, which we now call photons. Each photon carries a specific amount of energy determined by its frequency. High-frequency light, like ultraviolet or X-rays, has high-energy photons. Low-frequency light, like infrared or radio waves, has low-energy photons. This explained the photoelectric effect, where light hitting a metal surface ejects electrons, but only if the light frequency is above a certain threshold. Einstein won his Nobel Prize for this work, not for relativity. So a photon is created when something with energy, usually an electron in an atom or molecule, drops from a higher energy state to a lower energy state. The energy difference is converted into a photon with a specific frequency. The electron transitions between discrete energy levels, and poof, a photon appears, carrying away the excess energy at the speed of light. Now here's something wild. The moment that photon is created, it's immediately traveling at light speed, not accelerating to light speed, not building up to light speed. Instantly at light speed. There's no intermediate stage. Photons are never at rest. They can't be. They're always moving at exactly light speed from the instant they exist. And from the photon's timeless perspective, there is no instant they exist as a separate moment from the instant they're absorbed. It's all one event. When a photon is absorbed, the reverse happens. The photon's energy is transferred to an electron or another particle, which jumps to a higher energy state. The photon ceases to exist. It doesn't slow down and stop. It doesn't fade away. One instant it exists, traveling at light speed in its own timeless now, and the next instant it doesn't exist at all, having given up its energy to matter. But here's the question that should be bothering you. If a photon doesn't experience time, when does it decide to be absorbed? From our perspective, a photon might travel for billions of years before being absorbed. It passes by countless atoms, any of which could potentially absorb it. What determines when and where it gets absorbed? From the photon's timeless perspective, its emission and absorption are simultaneous, but from our perspective, there's a causal chain of events leading from emission to absorption. This gets at something deep in quantum mechanics called the path integral formulation, developed by Richard Feynman in the 1940s. Feynman showed that you can think of a photon not as taking a single path from emission to absorption, but is simultaneously taking every possible path. The photon that goes from the sun to your eye doesn't just travel in a straight line. It takes a path that goes to Mars and back. It takes a path that loops around Jupiter. It takes an infinite number of paths, each with its own probability amplitude. All these paths interfere with each other, some constructively, some destructively, and the sum of all possible paths gives you the probability of where the photon will end up. From this perspective, the photon doesn't decide anything along the way. The emission and absorption are boundary conditions, and everything between is this weird quantum superposition of all possibilities. The photon exists in a timeless state, connecting emission to absorption, and it's only when we try to measure or interact with it somewhere along the way that it collapses into appearing at a specific location at a specific time. This connects back to our discussion of the block universe. In some interpretations of quantum mechanics combined with relativity, the entire space-time history of the universe is a fixed four-dimensional structure, and quantum events don't happen in time. They're relationships between different parts of this structure. The photon isn't a little particle traveling through space and time. It's a connection, a relationship, a quantum correlation between an emission event and an absorption event in space-time. Mind blown yet? Because we're about to go even deeper. What does it mean that light has no mass? Here's a fact that might surprise you. Photons have no rest mass. Zero. Zilch. Nada. This isn't just a measurement limitation. Photons fundamentally, theoretically, must have zero rest mass. And this is intimately connected to why they must travel at the speed of light. In special relativity, there's a beautiful equation that relates energy, momentum, and mass. It's E squared equals P squared C squared plus M squared C to the fourth, where E is energy, P is momentum, M is rest mass, and C is the speed of light. This is actually the full version of Einstein's famous E equals mc. That famous equation is just the special case for something at rest where momentum is zero. For a photon, which has zero rest mass, this equation simplifies to E equals pc. Energy equals momentum times the speed of light. Even though a photon has no mass, it has both energy and momentum. This seems contradictory, right? How can something with no mass carry energy and momentum? The answer is that relativistic mass and rest mass are different things. Rest mass is the mass something has when it's not moving, its intrinsic mass. But in relativity, energy and mass are equivalent. Anything with energy has an effective mass due to that energy. For a photon, all of its mass is relativistic mass due to its energy in motion. It has no rest mass, no intrinsic mass, no mass in any reference frame where it's standing still, because there is no reference frame where it's standing still. And here's the kicker. Anything with zero rest mass must travel at the speed of light. Not can travel at light speed. Must travel at light speed. Always. In every reference frame. It's not a matter of how much energy you give it. A massless particle has no choice but to move at light speed. And anything with non-zero rest mass can never reach light speed, no matter how much energy you give it. Why? Because as you accelerate something with mass, it gets harder and harder to accelerate it further. As you approach light speed, the energy required to go just a little bit faster approaches infinity. You'd need infinite energy to accelerate a massive particle to light speed. This is why nothing with mass can reach or exceed light speed. It's not just a speed limit, it's an energy limit. But for a massless particle, this doesn't apply. With zero rest mass, there's no inertia to overcome. The particle doesn't accelerate to light speed. It exists at light speed. From the moment of creation, it's moving at c, and it will always move at c until it's absorbed. Now, you might be wondering, if photons have no mass, how can light be affected by gravity? This is where we need to transition from special relativity to general relativity. Special relativity deals with flat spacetime and reference frames moving at constant velocities. General relativity, which Einstein published in 1915, deals with curved spacetime and gravity. In general relativity, gravity isn't a force, it's the curvature of spacetime caused by mass and energy. Massive objects warp the fabric of spacetime, and things moving through that warped spacetime follow curved paths. Even though photons have no rest mass, they still follow the curvature of spacetime. They still take the shortest path, called a geodesic, through curved spacetime, which can be a curved path through space. This is why we can observe gravitational lensing. Light from distant galaxies bends around massive objects like galaxy clusters, creating multiple images or rings of light. The photons aren't being pulled by gravity in the Newtonian sense. They're following straight lines through curved spacetime. From the photon's timeless perspective, it's still traveling in a straight line, but that straight line is through curved four-dimensional spacetime, which appears curved when we project it onto three-dimensional space. British astronomer Arthur Eddington confirmed this prediction during a solar eclipse in 1919 by measuring how starlight bent around the sun. This made Einstein world famous overnight. The fact that light follows the curvature of spacetime was one of the first major confirmations of general relativity. But here's something really weird. In general relativity, light also experiences gravitational time dilation. A clock in a strong gravitational field runs slower than a clock in a weak gravitational field. Photons climbing out of a gravitational well lose energy. They become redshifted. Their frequency decreases. This is called gravitational redshift, and it's been measured countless times. But wait, if photons don't experience time, how can they experience time dilation? This seems like a contradiction. The resolution is subtle. Photons don't experience time, but they do connect different points in spacetime, and those points can be at different gravitational potentials. The photon itself doesn't experience the gravitational field, but the relationship between its emission event and absorption event is affected by the curvature of spacetime between those events. The photon's frequency at emission, as measured by an observer at the emission point, will be different from its frequency at absorption, as measured by an observer at the absorption point, if there's a gravitational field between them. This is getting into some really subtle territory, but stick with me, because what I'm about to tell you next will tie all of this together in a way that's going to completely reshape how you think about reality itself. Let's do a thought experiment. Imagine you could accelerate to higher and higher speeds, approaching the speed of light. What would you observe? Well, as you go faster, time dilation means that less time passes for you relative to the outside world. You could travel to a star 100 light years away, and from Earth's perspective, 100 years would pass. But if you're traveling close enough to light speed, from your perspective, the journey might take only 1 year. You'd age 1 year while Earth aged 100 years. Now imagine you keep accelerating, getting closer and closer to light speed. From your perspective, the journey time keeps getting shorter. At 99.9999% of light speed, that 100 light-year journey might take only a few days from your perspective. At 99.9999999%, maybe a few minutes. In the limit, as you approach exactly light speed, the journey time approaches zero. At exactly light speed, the journey takes zero time. But it's not just time that changes. As you go faster, distances in your direction of travel contract. That 100 light years gets shorter and shorter from your perspective. At high enough speeds, it might be only 1 light year, then a light month, then a light second. In the limit, as you approach light speed, the distance contracts to zero. Now, here's what's absolutely wild. From your perspective, you're always stationary, and the universe is moving past you. When you're on that spaceship going 99.999% of light speed toward a distant star, from your perspective, you're sitting still, and that star is rushing toward you at 99.99% of light speed. And because of length contraction, the distance between you and that star is contracted. The star is much closer to you than it is from Earth's perspective. This brings us to a profound realization. There is no absolute space. Just like there's no absolute time, there's no absolute distance. The distance between two objects depends on your reference frame. It's not that we're measuring it wrong or perceiving it differently. The distance itself is different for different observers. Space and time are observer dependent. Now, let's push this to the limit. What's the universe like from light's perspective? Well, time doesn't pass. All moments are simultaneous. Distance in the direction of travel is zero. The entire universe in that direction is compressed to a single point. The photon exists everywhere along its path simultaneously. It's emitted and absorbed at the same time and place. But here's something even more profound. What about the direction perpendicular to the photon's travel? Length contraction only happens in the direction of motion. Perpendicular to the motion, distances remain unchanged. So from the photon's perspective, the universe is like a flat disk perpendicular to its direction of travel, with zero thickness in the direction it's moving. It's two-dimensional, not three-dimensional. Except it's even weirder than that, because perspective implies a viewpoint over time, and light doesn't have time. It's not like the photon is seeing a two-dimensional universe. The photon doesn't see anything. It doesn't experience anything. It exists in a state so alien to our experience that all our language fails. But let me try to paint a picture anyway, because I think there's something profound here. Imagine you're reading a book. From your perspective, you read one page, then turn to the next page, then the next. You experience the story unfolding over time, but the book itself contains all the pages simultaneously. The entire story exists as a complete object. You could, in principle, flip to the end and read the last page first. The pages don't happen in sequence. They exist in sequence. The universe, from light's perspective, is like that book. All of spacetime exists as a complete, unchanging structure. There's no flow of time, no unfolding of events. Just the eternal existence of the entire structure all at once. This is the block universe taken to its logical extreme. And light, existing at the boundary of this structure, experiences, if we can even use that word, the ultimate version of this timeless reality. Now, some of you might be thinking, this is just a quirk of our mathematical description. Surely there's a real, objective reality underneath all this observer-dependent stuff. And that's a natural thought. But here's the thing. Every experiment we've ever done confirms that this observer dependence is real. It's not just mathematical formalism. Time dilation is measured. Length contraction is measured. The relativity of simultaneity is confirmed. Different observers genuinely disagree about what's happening now across the universe, and there's no objective fact of the matter about who's right. They're both right. This is one of the hardest things to accept about relativity. There is no underlying absolute reality that we're all perceiving differently. The observer-dependent reality is the reality. Space-time is fundamentally a relational structure. Events don't happen at absolute times and absolute locations. They happen at times and locations relative to other events, relative to observers, relative to reference frames. And light, massless and moving at the cosmic speed limit, is the ultimate expression of this. Light connects events in space-time, but it doesn't experience the journey between them. It's the thread that weaves the tapestry of space-time together, but it exists outside the temporal dimension of that tapestry. You might be wondering, does any of this actually matter for everyday life? Are these just abstract physics concepts that have no bearing on reality as we experience it? Hold that thought, because in the next section, we're going to bring this back down to Earth and explore why this actually changes everything about how you should think about your own existence. All right, we're about halfway through this journey, and I want to pause and connect this to you personally. Because you might be thinking, This is fascinating. But what does it have to do with me? I'm not a photon. I'm not traveling at light speed. I experience time passing. So why should I care about light's timeless existence? Here's why this matters. Understanding that light doesn't experience change forces you to confront the fact that your experience of reality is not the only valid perspective. It's not even necessarily the most true perspective. It's just one perspective among many possible perspectives. And once you truly grasp this, it changes how you think about everything. Let me ask you, what is time? You experience it as flowing from past to future. You remember yesterday. You experience now. You anticipate tomorrow. This seems fundamental, undeniable, obvious. But we've just seen that for light. Time doesn't flow at all. All moments are simultaneous. So which perspective is correct? Yours or light's? The answer is both, and neither. Time as a flowing river is a feature of your reference frame, your velocity through space-time, your perspective. It's no more or less real than light's timeless perspective. They're different views of the same underlying four-dimensional space-time structure. Think about what this means for your life. You worry about the future. You regret the past. You feel like time is slipping away, like you're running out of time. But from the block universe perspective, all moments of your life exist simultaneously. Your birth, your childhood, this moment right now, your death, all of it exists as a complete, unchanging structure. The you reading this sentence exists eternally in this moment. The you as a child exists eternally in that moment. All the yous at all the moments are equally real, all existing simultaneously in space-time. This doesn't mean your choices don't matter. The future is still uncertain from your perspective because you don't have access to your future self's information yet. You still experience time flowing, still make decisions, still shape your life. But it does mean that the anxiety about time running out is based on a limited perspective. In the block universe, you're not running out of time. You exist across time. Your entire temporal existence is a complete, four-dimensional object. Now, I'm not saying you should abandon all sense of urgency or purpose. What I'm saying is that understanding the physics of time and light can give you a different relationship with your own existence. You're not just a fleeting moment in an unstoppable flow of time. You're a four-dimensional structure in space-time, extended across time just as you're extended across space. Every moment of your life is a slice of that structure, and all the slices together make up the complete you. Light, in its timeless state, connects all these moments. The light that hit your eyes when you were born, and the light hitting your eyes right now, are both part of the same timeless structure of electromagnetic radiation, weaving through space-time. Photons don't distinguish between past, present, and future. They connect all moments simultaneously. And here's something else to consider. Every photon that enters your eyes is giving you information about the past. Even light from something right in front of you took a tiny amount of time to reach you. You're always seeing the past, never the present. The sun you see is the sun as it was 8 minutes ago. The stars you see are as they were years, decades, centuries, or even millennia ago. Some of the stars you see at night don't even exist anymore in the present, but their light is still traveling toward us, carrying information about a past that no longer exists. But from the photon's perspective, all of this is simultaneous. The emission and the absorption are the same event. The star exploding billions of years ago, and you seeing that light tonight are the same moment in the photon's timeless reference frame. Past and future collapse into an eternal now. This has profound philosophical implications. If the block universe is correct, if all of space-time exists as a complete unchanging structure, does that mean the future is predetermined? Do you have free will? This is a question that physicists and philosophers have debated for over a century, and there's no consensus answer. Some argue that the block universe implies determinism. If the future already exists, then it's already determined. Your choices are already made, even if you haven't experienced making them yet. From this view, free will is an illusion created by your limited perspective as you move through time. Others argue that quantum mechanics saves free will. Quantum events are genuinely random, not predetermined. The future isn't a single fixed block. It's a branching structure of probabilities that collapse into actualities as observations are made. In this view, the block universe exists, but it's constantly growing as quantum events determine which branch of possibility becomes reality. Still, others argue that free will and determinism aren't actually in conflict. You make genuine choices, and those choices shape which path through the block universe your world line takes. The fact that the path exists as a complete structure doesn't negate the agency you exercised in determining what that path would be. I don't have a definitive answer to the free will question, but what I do know is that understanding relativity and the timeless nature of light gives you a new framework for thinking about these ancient philosophical questions. It grounds them in physics rather than pure speculation, and it forces you to confront the strangeness of existence itself. Because here's the really wild part. You are made of atoms, which are made of electrons and quarks. And all of these particles interact by exchanging photons and other force-carrying particles. The electromagnetic force that holds your atoms together works by constantly exchanging virtual photons between charged particles. These virtual photons exist in quantum superposition, popping in and out of existence, carrying forces but existing in their own timeless reference frames. In a very real sense, the timeless nature of light is woven into the structure of your body, your brain, your consciousness. You are a pattern of matter and energy held together by timeless quantum interactions, moving through space-time one moment at a time from your limited perspective, but existing as a complete four-dimensional structure from a more comprehensive view. Does your head hurt yet? We're going to take all of this even further, because we haven't even touched on what happens when you combine quantum mechanics with relativity to create quantum field theory. And that's where things get truly bizarre. Let me blow your mind with something that sounds like science fiction, but is actually cutting-edge physics. There's no such thing as a photon. Or rather, photons aren't particles in any sense you're familiar with. They're excitations of an underlying field that permeates all of spacetime. Welcome to quantum field theory. Here's how physicists like Paul Dirac, Richard Feynman, and Julian Schwinger revolutionized our understanding in the 1940s and 50s. Instead of thinking of particles as little balls flying through empty space, we now understand that all of spacetime is filled with quantum fields. There's an electromagnetic field, an electron field, a quark field, and so on. These fields are the fundamental reality. Particles are just localized excitations, waves, or ripples in these fields. Think of it like a still pond. The water is the field. When you drop a stone in, ripples spread out. Those ripples are like particles. The ripples have energy. They move. They can interact with other ripples. But the ripples aren't separate things floating on the water. They're excitations of the water itself. The water is always there, filling the entire pond. The ripples are just temporary patterns of energy moving through the water. That's what a photon is. It's a ripple in the electromagnetic field. The electromagnetic field exists everywhere, in every point of spacetime, always. A photon is just a particular pattern of excitation in that field, a quantum of electromagnetic energy. And here's the wild part. That excitation, that photon, doesn't have a precise location. It's spread out as a wave in the field. It has a wavelength, a frequency, but not a definite position until it interacts with something else. This resolves something that might have been bothering you. If a photon doesn't experience time or distance, how does it know where to go? How does it get from point A to point B if from its perspective there's no journey? The answer is that it's not a little particle making a journey. It's a wave in a field, and that wave propagates according to the field equations. Maxwell's equations for electromagnetism. The wave spreads out, following all possible paths simultaneously in quantum superposition, and when it interacts with matter, the wave function collapses and a photon appears at a specific location. From the photon's timeless perspective, this all happens instantaneously. The wave is emitted, propagates, and is absorbed as a single timeless event. But from our time-experiencing perspective, we see the wave spreading out. We can calculate probabilities of where it might be detected, and we observe that it took time to travel from source to detector. Now, here's where it gets even more bizarre. In quantum field theory, the vacuum-empty space isn't actually empty. It's a seething foam of quantum fluctuations. Virtual particles constantly pop in and out of existence everywhere, all the time. Virtual photons, virtual electron-positron pairs, all kinds of virtual particles, appearing and disappearing so quickly that they don't violate conservation of energy, thanks to Heisenberg's uncertainty principle. These virtual particles are real in the sense that they have measurable effects. They cause tiny shifts in atomic energy levels, called the Lamb shift, confirmed by Willis Lamb in 1947. They cause a tiny attractive force between metal plates in a vacuum, called the Casimir effect, first measured by Marcus Sparnay in 1958. They contribute to the anomalous magnetic moment of the electron, which has been calculated and measured to extraordinary precision. They agree to better than 1 part in a trillion, making it one of the most precisely verified predictions in all of physics. But here's the thing about virtual photons. They don't travel at the speed of light. They can't. They exist for such a short time and travel such a short distance that they're not constrained by the usual relationship between energy, momentum, and mass. They're off-shell, as physicists say. They violate E equals PC squared plus MC squared, but only temporarily, only by an amount allowed by quantum uncertainty. Real photons, the ones that propagate over macroscopic distances, the ones we detect, the ones that travel from stars to our eyes, those must be on-shell, satisfying the energy-momentum relation. And those photons must travel at exactly light speed and must have zero rest mass. And those photons exist in the timeless state we've been discussing. But the quantum field theory picture adds a new layer of weirdness. The photon is an excitation of a field that exists everywhere. In some sense, the field itself is timeless. It's a structure that exists throughout all of spacetime. Excitations in that field photons propagate at light speed from our perspective, but exist timelessly from their own perspective. The field is the fundamental reality, and photons are patterns in that reality. This connects to something profound about the nature of existence. We tend to think of objects as primary and relationships as secondary. You exist, I exist, and we have a relationship. Objects first, relationships second. But quantum field theory suggests the opposite. Fields and their interactions are primary, and what we call particles are just patterns in those interactions. Relationships are fundamental, and objects emerge from relationships. And light photons are the carriers of the electromagnetic interaction. They are literally the relationship between charged particles. When two electrons repel each other, it's because they're exchanging virtual photons. The electromagnetic force is the exchange of photons. Light isn't just something that travels through space. It's the mechanism by which charged particles interact, the relationship that binds atoms together, the force that makes chemistry and biology possible. And all of this happens timelessly, from the photon's perspective. The entire structure of electromagnetic interactions across all spacetime exists as a timeless pattern in the electromagnetic field. We perceive it as unfolding over time, but that's because we're moving through time, sampling different slices of the complete spacetime structure. So when I said earlier that you're held together by timeless quantum interactions, I wasn't being poetic. I was being literal. The electrons in your atoms are constantly exchanging virtual photons with the nuclei, And those photons exist in a timeless state. The chemistry that makes your body work, the neural signals in your brain that allow you to think and perceive, all of it is mediated by photons that don't experience time. You are, quite literally, a pattern in space-time held together by timeless forces. Your experience of time flowing is an emergent property of how you, as a complex structure, interact with the quantum fields that permeate space-time. But at the fundamental level, the stuff you're made of and the forces that hold you together exist in a timeless quantum state. Are you starting to see how radically different reality is from our everyday perception? We're going to go even deeper, because we haven't talked about what happens when massive objects warp space-time so severely that not even light can escape. We need to talk about black holes. Black holes are perhaps the most extreme environments in the universe, and they reveal something profound about light and time. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from inside a boundary called the event horizon. The fact that light cannot escape a black hole tells us something deep about the relationship between light, space-time curvature, and causality itself. Karl Schwarzschild, a German physicist serving in World War I, derived the first exact solution to Einstein's general relativity equations in 1916, just months after Einstein published the theory. Schwarzschild's solution describes the space-time geometry around a spherical, non-rotating mass. And it revealed something shocking. If you compress enough mass into a small enough volume, space-time becomes so warped that you create a region from which nothing can escape, a black hole. The event horizon is not a physical surface. It's a mathematical boundary in space-time, defined by the property that any light emitted inside it cannot reach the outside universe. Light emitted exactly at the horizon stays at the horizon. Light emitted just inside the horizon is pulled inward. Only light emitted outside the horizon can escape to infinity. But here's what's weird. From the perspective of someone falling into a black hole, nothing special happens when you cross the event horizon. There's no physical barrier, no warning sign, no discontinuity. You just keep falling. But from the perspective of someone watching from far away, something very strange happens. As you approach the event horizon, time dilation becomes extreme. The light from your falling body becomes increasingly redshifted. You appear to slow down, approaching the horizon asymptotically, taking infinite time to actually cross it. From your perspective, you cross the horizon in finite time. From the external observer's perspective, you never cross it. You approach it for all eternity, frozen at the boundary. Both perspectives are valid. This is relativity taken to the extreme. Now, what about light itself? A photon approaching the event horizon from the outside can cross it. But once it crosses, it can never come back out. From the photon's timeless perspective, its journey from outside the black hole to the singularity at the center happens instantaneously. It's emitted outside the horizon and absorbed at the singularity in the same timeless moment. But here's something even more profound. Near a black hole, space-time is so warped that the paths light can take, the null geodesics, as they're called, behave very strangely. Outside the event horizon, light can orbit the black hole at what's called the photon sphere, a spherical surface where photons travel in circular orbits. Any photon launched tangentially at exactly the photon sphere distance will orbit forever. A tiny bit closer, and it spirals into the black hole. A tiny bit farther, and it spirals away. This means that if you could stand at the photon sphere, you can't. Actually, but let's pretend. You could theoretically see the back of your own head. Light from the back of your head would travel all the way around the black hole and back to your eyes. Of course, you'd also be experiencing insane gravitational forces and time dilation. But the point is that light's path through space-time can be so warped that it loops back on itself. And inside the event horizon, things get truly bizarre. The mathematical structure of space-time inside a Schwarzschild black hole is such that the radial direction, toward and away from the center, becomes time-like, and the time direction becomes space-like. This means that once you're inside the horizon, moving toward the singularity is like moving toward the future. You can no more avoid hitting the singularity than you can avoid moving forward in time outside the black hole. The singularity isn't a place in space, it's a moment in your future. And light? Photons inside the event horizon are also destined for the singularity. All their light cones point inward. Every possible path they could take leads to the singularity. From their timeless perspective, emission and absorption at the singularity are simultaneous. But the structure of space-time has become so warped that toward the center and toward the future are the same direction. This reveals something profound. Light doesn't just move through space-time. It defines the structure of causality itself. The paths light can take define what can causally influence what. If you can't send a light signal from event A to event B, then A cannot causally affect B. Light defines the boundaries of cause and effect. The event horizon is the boundary where this causal structure breaks down for external observers. Information from inside cannot causally influence the outside. The black hole is causally disconnected from the rest of the universe. And this is defined by light, by which paths photons can and cannot take through curved spacetime. Stephen Hawking discovered in 1974 that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. Virtual particle pairs pop into existence right at the horizon. Normally, virtual pairs annihilate immediately. But at the horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real Hawking radiation. To an outside observer, the black hole is slowly evaporating, emitting photons and other particles. What's wild about Hawking radiation is that it's thermal. It has a temperature inversely proportional to the black hole's mass. A stellar mass black hole has a temperature of a few billionths of a degree above absolute zero, far colder than the cosmic microwave background. But a microscopic black hole would be incredibly hot, eventually evaporating in a burst of high-energy radiation. And here's the thing. Those Hawking photons don't experience time either. They're emitted at the horizon in a timeless moment from their perspective. But from our perspective, they carry away energy and information from the black hole over billions or trillions of years. The timeless photons are the mechanism by which black holes eventually return their information to the universe. This creates a paradox called the black hole information paradox. Quantum mechanics says information cannot be destroyed. But if you throw a book into a black hole, and the black hole eventually evaporates into thermal radiation, where did the information in the book go? Thermal radiation is random. It doesn't encode specific information. This paradox has driven much of theoretical physics research for the past 50 years, leading to ideas like holography and the suggestion that information is encoded on the event horizon itself. Light is at the heart of this paradox. Photons carry information. Hawking photons carry energy away from black holes. But do they carry information? And how does information that fell past the event horizon get encoded into photons that are emitted at the horizon? These questions are still being debated. But regardless of the resolution, the fact remains. Light, in its timeless state, is the messenger that connects different regions of spacetime, that carries information and energy, that defines causality itself. Even in the most extreme gravitational environments, light's special status remains. It's the boundary between what can exist and what cannot, between what can escape and what is forever trapped. And you, sitting there watching this video, are receiving photons from your screen that traveled a tiny distance in a tiny amount of time from our perspective, but zero distance in zero time from the photon's perspective. Every photon bringing you this information exists in a timeless state, connecting the screen to your retina in a single eternal moment. Let's push even further. What does cosmology tell us about light and time? The universe is 13.8 billion years old. We know this because we can observe light from the early universe, the cosmic microwave background radiation, emitted when the universe was only 380,000 years old. This light has been traveling toward us for 13.8 billion years. It's the oldest light we can see, the earliest snapshot of the universe we have access to. But here's the question. From the perspective of those photons, how much time has passed? 0. From their timeless reference frame, their emission in the hot dense plasma of the early universe and their absorption in our telescopes today are the same event. No time elapsed. The entire 13.8 billion year history of the universe, from the cosmic microwave background's emission until now, is a single timeless moment for those photons. Let that sink in. The cosmic microwave background photons don't remember the early universe. They don't carry a temporal record. From their perspective, they're being emitted and absorbed simultaneously. The vast expanse of cosmic time is an illusion of perspective, our perspective, moving through time at subliminal speed. The cosmic microwave background is almost perfectly uniform across the entire sky, with only tiny temperature fluctuations of about 1 part in 100,000. These tiny fluctuations are the seeds of all structure in the universe, galaxies, stars, planets, you. But from the perspective of the CMB photons, all of that structure formation hasn't happened yet, or has already happened, or is happening simultaneously. Past, present, and future are meaningless concepts in the photon's timeless existence. Now let's think about the expansion of the universe. The universe is expanding, meaning that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This was discovered by Edwin Hubble in 1929. The expansion isn't galaxies moving through space. It's space itself expanding, carrying galaxies along with it. Light traveling through expanding space gets stretched. Its wavelength increases, shifting toward the red end of the spectrum. This is cosmological redshift, and it's how we measure distances to distant galaxies. The more redshifted the light, the farther away the source, and the longer the light has been traveling. But here's the thing. The photon doesn't experience this journey. From its perspective, emission and absorption are simultaneous. Yet the photon clearly has a different wavelength when absorbed than when emitted. The redshift is real and measurable. How do we reconcile this? The resolution is that the redshift isn't something that happens to the photon during its journey. The redshift is a relationship between the state of the universe at emission and the state of the universe at absorption. The photon connects these two states, but it doesn't experience the transition between them. The wavelength we measure depends on both the emission event and the absorption event, and the expansion of spacetime between these events is encoded in that wavelength. But the photon itself exists timelessly, connecting past and present in a single moment. This gets even weirder when you consider the cosmological horizon. There are galaxies so far away that their light hasn't had time to reach us yet. We can't see them. They're beyond our cosmological horizon. But light from those galaxies is on its way. In the future, we'll be able to see them as their light finally reaches us. From our perspective, that light has been traveling for billions of years. From the photon's perspective, no time has passed. And then there's the ultimate cosmological horizon, the future edge of the observable universe. Because the universe is expanding, and the expansion is accelerating, there are galaxies moving away from us, so fast that their light will never reach us, no matter how long we wait. They're receding faster than light can travel toward us. These galaxies are beyond what's called the event horizon of our observable universe, and we will never, ever receive any information from them. From our perspective, those galaxies are forever inaccessible, locked beyond a boundary we can never cross. But from the perspective of a photon emitted by one of those galaxies toward us, it's traveling at light speed, experiencing no time, connecting its emission point to where, if the photon never reaches us, What defines its absorption? This is an open question in cosmology. Some physicists argue that the photon must be absorbed somewhere, eventually, even if it's by intergalactic dust or gas. Others suggest that the photon might exist in a perpetual state of propagation, never being absorbed, existing timelessly forever. But there's an even more profound implication. The universe might be spatially infinite. If it is, then there are infinitely many galaxies, infinitely many stars, infinitely many photons being emitted in every moment. And from the timeless perspective of those photons, all of that infinite emission and absorption happens simultaneously. The entire infinite universe, across all of cosmic time, is a single timeless event from light's perspective. This connects back to the block universe. If spacetime is a four-dimensional structure containing all events from Big Bang to ultimate end, and if we include the entire possibly infinite spatial extent of the universe, then the block universe is inconceivably vast. And yet, from light's perspective, it's all one timeless moment. Every photon ever emitted and absorbed, everywhere in the possibly infinite universe, across all 13.8 billion years of cosmic history, and whatever future awaits us, all of it is a single timeless now in the reference frame of light. Doesn't that make you feel simultaneously infinitesimally small and cosmically connected? You're made of atoms that formed in stars billions of years ago. Those stars emitted light that traveled across the cosmos for eons. Some of that light hit Earth and powered photosynthesis, creating the food chain that eventually led to you. You are, quite literally, made of stardust brought together by eons of cosmic evolution. But from the perspective of the light that made it all possible, no time passed. The stars, the planets, the evolution of life, your birth, this moment, all of it is connected in a timeless web of causality mediated by light. Now, let me address something that might be bothering you. If light doesn't experience time, does that mean consciousness of time is an illusion? Are we wrong to feel like time is passing? This is where physics meets philosophy meets neuroscience, and we need to tread carefully. Your experience of time passing is real. The fact that photons don't experience time doesn't invalidate your experience. But it does reveal that temporal experience is perspective dependent. Time is not an absolute river flowing uniformly for everyone everywhere. It's a dimension of space-time that different observers navigate differently depending on their motion and the gravitational fields they're in. Consciousness and the experience of time is one of the deepest mysteries in science. How do we experience the present moment? Why does time seem to flow in one direction? Why do we remember the past, but not the future? These questions touch on the nature of consciousness itself, and we don't have complete answers. But physics gives us some clues. The arrow of time, the direction from past to future, is closely tied to entropy. The second law of thermodynamics states that entropy, roughly speaking, disorder, always increases in a closed system. The universe started in a very low entropy state at the Big Bang, and has been increasing in entropy ever since. This gives time a direction. Entropy increasing defines which way is future and which way is past. Your consciousness, your brain, your memories, all of these are physical processes that involve increasing entropy. When you form a memory, you're creating a correlation between brain states and past events, and this process increases entropy. You can remember the past because past states left physical traces, memories, records, fossils. You can't remember the future because future states haven't left traces yet. The arrow of time in your consciousness is the arrow of entropy. But light doesn't care about entropy. A photon emitted and absorbed is a reversible process. You can run the equations backward and get a perfectly valid solution. Time reversal symmetry holds for electromagnetism at the fundamental level. The arrow of time emerges only when you have many particles, many interactions, statistical behavior that leads to increasing entropy. So in a sense, light exists outside the thermodynamic arrow of time. It connects moments in space-time without regard for which direction is past and which is future. The photon is emitted and absorbed, and from its perspective, these are the same event, not two events with one before the other. Now, let's talk about perception. Everything you see is brought to you by photons entering your eyes. The image of the world you construct in your mind is based entirely on information carried by light, but that information always comes from the past. Light takes time to travel from our perspective, so you're always seeing things as they were, not as they are. This delay is usually imperceptible. Light travels so fast that the delay between someone across the room and your perception of them is only a few nanoseconds. Your brain can't process information that quickly anyway, so this delay doesn't matter. But for distant objects, it matters a lot. The sun you see is 8 minutes old. The nearest star, Proxima Centauri, you see it as it was 4.24 years ago. The Andromeda galaxy you see is 2.5 million years old. Some of the galaxies we observe in deep space are so far away that we're seeing them as they were when the universe was less than 1 billion years old. We're looking back in time every time we look at the sky. We're observing the past. We're receiving messages sent billions of years ago, and those messages traveled in the form of photons that experienced no time during their journey. The photon left a galaxy 10 billion years ago and arrived at our telescope last night, and from the photon's perspective, these events are simultaneous. This means that in a very real sense, the universe's past and present are connected by timeless messengers. The light from the early universe is still arriving. The cosmic microwave background is everywhere, a relic of the Big Bang's afterglow, surrounding us, passing through us constantly. You're bathed in photons that were emitted in the first moments of the universe, and those photons don't experience any temporal separation from their emission to now. But here's something that will really bend your mind. Because of the finite speed of light and the vast distances in space, different observers see different versions of now across the universe. The relativity of simultaneity means that there's no objective present moment that extends across the cosmos. Your now includes events on Alpha Centauri happening 4.37 years in Earth's future or past, depending on your velocity. An alien on a planet in a distant galaxy, moving at high speed relative to us, would consider events in Earth's past or future to be happening now from their perspective. There's no cosmic now. There's only local now, what's happening in your immediate vicinity. And light, connecting all these different local nows, exists outside of this framework entirely. Light is the messenger that tells us about other places and other times, but it doesn't participate in time itself. Think about what this means for your perception. When you look at the night sky, you're not seeing the universe as it is. You're seeing a patchwork of different moments in the universe's past, all stitched together by your brain into a coherent image. That star is as it was 500 years ago. That nebula is as it was 1,000 years ago. That galaxy is as it was 50 million years ago. You're observing events that, from Earth's frame of reference, are separated by millions of years. But from the photon's perspective, they're all simultaneous with your observation of them. Your entire visual perception of reality is mediated by timeless photons, carrying information from different moments in cosmic history. And your brain assembles this into the illusion of a coherent present moment. The now you experience is a constructed narrative, a story your brain tells itself by integrating information from countless photons, each of which exists in its own timeless state. Does this diminish the reality of your experience? No, your experience is real, but it reveals that your experience is a perspective, one among many possible perspectives, shaped by your reference frame, your velocity, your location in spacetime. And understanding this can give you a profound sense of humility and wonder. You're not experiencing objective reality. You're experiencing your reality, filtered through the physics of light and perception. Let me connect this to something practical. Have you ever had an experience where time seemed to slow down? During an accident, A moment of danger? A profound experience? People often report that time dilates subjectively during intense moments. This isn't relativistic time dilation. You're not moving fast enough for that. This is psychological time dilation, where your brain's processing of events changes your perception of duration. But the fact that subjective time can be stretched or compressed reveals something important. Time as you experience, it is constructed by your brain. It's not a direct readout of some objective clock. Your brain is interpreting signals, building narratives, creating the experience of temporal flow. And physics tells us that even objective time is relative, observer-dependent. So time, at both the physical and psychological levels, is not what common sense tells us it is. All right, stick with me, because we're entering the home stretch, and I'm going to tie all of this together in a way that will completely reframe everything we've discussed. Let's zoom out and ask the biggest question of all. What does the timeless nature of light tell us about the ultimate nature of reality? We've journeyed from special relativity to general relativity, from quantum field theory to cosmology, from black holes to conscious experience. And throughout all of this, one thing has remained constant. Light is special. Light is the boundary, the limit, the defining feature of space-time structure itself. Einstein once said, "For the rest of my life, I will reflect on what light is." He spent his later years searching for a unified theory, a single framework that could explain all of physics. He never found it. But his insight that light is fundamental, that understanding light means understanding the structure of reality itself, was prophetic. Modern physics has only deepened this insight. In string theory, one of the leading candidates for a theory of quantum gravity, the fundamental constituents of reality aren't particles but tiny vibrating strings. Different vibration modes of these strings correspond to different particles, and one of the vibration modes corresponds to the photon. Light emerges from the deepest level of string theory as a fundamental excitation mode of the underlying structure. In loop quantum gravity, another approach to quantum gravity, space-time itself is quantized at the Planck scale, the unimaginably small scale of y-35 meters and y-43 seconds. At this scale, space-time is a network of quantum relationships, a spin network where nodes and links carry quantum information. And the propagation of light through this quantum space-time is one of the key phenomena the theory seeks to explain. In theories of quantum cosmology, the entire universe is described as a quantum wave function evolving according to the Wheeler-DeWitt equation. In these frameworks, time might be emergent rather than fundamental. The universe as a whole might not exist in time, but rather contain time as a feature of certain quantum states. And light, connecting events across this quantum spacetime, plays a central role. In all these cutting-edge theories, light isn't just a phenomenon to be explained. It's a fundamental aspect of the theory itself. Light defines causality. Light defines the speed limit of information. Light defines the structure of spacetime. You can't build a theory of reality without accounting for light. And accounting for light inevitably leads you to relativity, to spacetime, to the observer-dependent nature of reality. And this brings us to a profound philosophical point. Reality is relational. There are no absolute properties, no objective facts that exist independent of observers and reference frames. What's here and what's there, what's now and what's then, what's simultaneous and what's sequential, all of these depend on your reference frame. Physics doesn't describe an absolute reality existing independent of observation. It describes relationships between events, correlations between measurements, structures that remain invariant under transformations between reference frames. Light, in its timeless existence, is the ultimate expression of this. Light doesn't have its own independent existence in time. It exists only in relationship to other things, its source and its detector, its emission and its absorption. The photon is not a thing traveling through time. It's a connection, a relationship, a quantum correlation between two events in spacetime. This relational view of reality is profound. It means that you can't understand anything in isolation. Everything is defined by its relationships to other things. An electron isn't a little ball with inherent properties. It's a pattern of quantum fields, defined by how it interacts with other fields. A photon isn't a particle with a trajectory. It's an excitation in a field, defined by its emission and absorption, existing in superposition across all possible paths. And you? You're not an isolated entity separate from the universe. You're a pattern in spacetime, a structure of matter and energy, defined by your relationships to everything else. The atoms in your body came from stars. The energy that powers your thoughts comes from food, which ultimately comes from sunlight. The information you receive about the world comes from photons entering your eyes. You are deeply, fundamentally, inextricably connected to the entire cosmos. And the timeless nature of light is part of what makes this connection possible. Photons don't age, don't decay, don't experience time. They can travel across the entire universe, billions of light years, billions of years from our perspective, connecting the distant past to the present, carrying information from one edge of the cosmos to the other, all without experiencing a single moment of that journey. Light is the ultimate messenger, the universal connector, the thread that weaves the tapestry of space-time together. Subramanian Chandrasekhar, the astrophysicist who worked out the physics of white dwarfs and won the Nobel Prize in 1983, once reflected on the beauty of general relativity. He said, "The pursuit of science has often been compared to the scaling of mountains, high and not so high. But who amongst us can hope, even in imagination, to scale the Everest and reach its summit when the sky is blue and the air is still, and in the stillness of the air survey the entire Himalayan range and the dazzling white of the snow stretching to infinity? None of us can hope for a comparable vision of nature and of the universe around us. But there is nothing mean or lowly in standing in the valley below and awaiting the sun to rise over Kanchenjunga. Understanding that light never experiences change is like getting a glimpse of that Himalayan range. It's a view of reality that most people never see, a perspective that reveals the strange, beautiful, unified structure of spacetime. And even if we can't fully grasp it, even if our time-bound minds can't truly comprehend timelessness, even attempting to understand it elevates us. It makes us realize how limited our everyday perspective is, and how much more there is to reality than what we directly perceive. So what's the takeaway from all of this? What should you do with this knowledge? Here's what I think. Embracing the timeless nature of light should make you humble and curious. Humble because it reveals how limited your perspective is. You experience time flowing, but that's just your reference frame. You experience a present moment, but there's no objective present extending across the cosmos. You see the world as solid and unchanging, but it's made of quantum fields in constant flux, held together by forces mediated by massless particles that don't experience time. And curious because if light can be so radically different from your intuition, what else might be different? What other features of reality might be nothing like what they seem? The universe is stranger than we imagine. It might be stranger than we can imagine. And that's exciting. That's a reason to keep questioning, keep learning, keep pushing the boundaries of understanding. Light never experiences change. And somehow, in that timeless existence, light makes change possible for the rest of us. Photosynthesis, vision, information transfer, the warming of planets, the radiation of stars, all of it depends on light. Life depends on light. Consciousness depends on light. You depend on light. And yet, light itself exists outside the temporal framework that makes your existence meaningful. There's a poetry to that, a profound irony. Light enables time without experiencing time. Light connects moments without existing across moments. Light is the medium through which change happens, yet light itself is unchanging, timeless, eternal. As you go about your life, receiving photons with every glance. I want you to remember, those photons are timeless messengers. They connect your present to sources in the past, but from their perspective, past and present are one. The light from the sun warming your face is 8 minutes old from your perspective, but 0 seconds old from the photon's perspective. The ancient starlight you see at night has traveled for centuries or millennia from your perspective, but 0 time from the photon's perspective. You are surrounded by timelessness. You are bathed in eternity. Every moment of your time-bound existence is interwoven with the timeless existence of light. And understanding this, truly grasping it, should fill you with awe. Because you're not just a biological organism experiencing time. You're a 4-dimensional pattern in space-time, connected to the entire cosmos by timeless forces and timeless light. You're part of something vast, something beautiful, something strange and wonderful beyond measure. You're made of star stuff, powered by light, conscious because of quantum processes that don't experience time the way you do. And that's the ultimate lesson of light's timeless existence. Reality is not what it seems. Your everyday experience, as real as it is to you, is a limited slice of something far grander and far stranger. The universe is a 4-dimensional space-time structure where past, present, and future exist together. You're a temporary pattern in that structure, experiencing one moment after another, but the totality of you, all your moments, exists eternally in space-time. Light doesn't experience change because light exists at the boundary of space-time structure, at the cosmic speed limit where time stops and distance vanishes. And in doing so, light reveals the truth, that time and space are not absolute containers in which things happen, but relative dimensions woven together into a unified space-time, experienced differently by different observers, yet forming a coherent mathematical structure that we can understand, predict, and marvel at. Einstein gave us the framework. Countless physicists have filled in the details. And now you know something that most people never think about. Light, the most familiar phenomenon, the thing that lets you see, is also the most alien thing in the universe. It doesn't experience anything. It exists in a timeless now, connecting all of space-time in a web of electromagnetic relationships that make chemistry, biology, consciousness, and life possible. The next time you see a ray of sunshine, or gaze at the stars, or even just glance at your screen, remember, those photons are timeless. They're eternal. They connect you to the cosmos in ways that transcend time itself. And you, as a pattern of matter and energy held together by timeless forces and mediated by timeless light, are part of that eternal structure. You're not just in the universe. You're of the universe. You're made from it, powered by it, connected to all of it through light that never experiences change. And maybe, just maybe, understanding that can help you see your own life differently. Not as a race against time, but as eternal 4-dimensional structure in space-time. A pattern that exists across time rather than within it, experiencing itself one moment at a time, but existing as a complete whole in the timeless mathematics of space-time. That's the final revelation. You're not just watching the universe unfold. You're part of its eternal structure. And the light that never experiences change is what connects you to everything else that has ever been and ever will be. Past, present, and future, all woven together by timeless photons into the magnificent tapestry of reality. Thank you for taking this journey with me. If your mind has been blown, if you've seen reality in a new way, if you've felt even a fraction of the wonder I feel about these ideas, then this was worth it. Do me a favor. Like this video, subscribe to the channel, and share this with someone who loves thinking deeply about the universe. And down in the comments, tell me, has this changed how you think about time and light? Where are you watching from? And what time is it there? Because unlike light, we're all experiencing time together right now, even though our nows are just limited perspectives on an eternal space-time structure. Keep questioning, keep wondering, keep seeking that glimpse of the Himalayas. because the universe is waiting to blow your mind, one timeless photon at a time.